Shout out to my boy Resonance, assigning frequencies to various objects based on their ability to vibrate. This one goes out to you. I got 2 words for you all. This is what I'm all about right here. Them standing waves. When I hit that perfect reflection, the sound gives the whole world an erection. Your rhymes are weaker than one direction, and when you go out, you don't need to bring protection, because I be making nodes, places where the particles don't move, leaving your ass looking like a toad. It's on, son, lock and load. You better hit the road, because my antidotes have these particles go over the top. They can't stop moving to the beat of my breath, so knock your ass to death. The sound so loud it will make you deaf. It's most deaf. Just ask anyone from Tupac to Mos Def. I am the best. Leave you with the rest. I'm about to put you to the test, son. You ain't got none, so let's have some fun. Woo! Drop the mic!
I ain't gotta shout out, this is 100% true. You may rap fast, but you gotta get ready for this blast of light. You know it's gonna be tight coming through the night. I got that kind of speed that will give you a nosebleed. Nothing will ever be faster than me. I'll turn your whack ass backwards with my words, like the images of a flat or concave mirror. Flipping on your y-axis, hanging you upside down with the masses of dead meat. I'll leave you strung up in the heat that I'm making. Won't be long till you're baking. When you're quaking, I'll hit you with the convex mirror to make you look a whole lot queer. Flipping you on your x-axis, making you look a whole lot near, but really you're just stressed.
Alright, sure you're faster than me, but I can still change pitch by altering frequency, so I can whoop your ass in alto, basso, or soprano. On the guitar, when you shorten that string, the pitch will make your ears sting. How you might say, well, I know this sounds cray, but when you change the length, tension, or density of a string, then the wavelength changes and the frequency goes up or down. The shift so fast, it will make you drown in the sound of your world crashing. Because when I'm blasting, I make the earth quake and shake. Everybody fears me and nobody comes near me, except for your mama. I had her down in the Bahamas with my llama.
Oh, hell no. You think you'd be looking better than me? Ha! I'm more than any other guy. When I go by, the girls be like, oh me, oh my. I got that white light that can shine through the night. I can be every color in the rainbow and still enough to make it rain, yo. My boys Pink Floyd will kill your sinusoids when I hit them prisons. You know I never be missing them. It's no surprise that females got that aversion towards my dispersion. You get a full rainbow, the Roy G. Bit. Leaves me with a lot of love to give, a lot of honeys to live. Your sounds are weak, your voice is meek. All week long I'm like a lion. You acting like you're dying. Your face leaves baby crying while in the bedroom leaving their mama's sign. Get out of here, Holmes.
Alright, I hope you all like that rap video. Now we're just gonna go over some of the physics of concave and convex mirrors and their light. Alright, so here you can see clearly that we have a diagram of a convex mirror. It's called a ray diagram. It shows the reflections and it shows where the image is made. See, now this is a convex mirror, and you cannot project an image directly from a convex mirror onto a screen, you see, because if you look right there, you see that the image curve behind the curvature. Behind the curvature, right, okay, curvature here of the convex mirror. Here's your image. Here would be your projected screen, and you cannot project upon the screen because there's no actual image there that you can actually see. Now, where the image occurs, see the object here, and you see reflections. The image where that occurs is typically called the focal point, or where all of the rays kind of intersect, right? But see, that can't happen here. And that's why I don't know what else I'm supposed to talk about. You can't project an image onto a direct screen with this mirror. There's something about the curvature. You see that the curvature occurs here, the image occurs back here, and yes. Next. However, when you have a concave mirror, as you see here, you can project an image onto a screen. You see, we have our focal point inside the curvature of the mirror, so you have your reflection. The focal point occurs here, which means that the image will also occur here, which means that you can project this onto screen. Now, take a good look at that. Moving on. Now, the hip-hop video you just watched does not quite properly cover how to vary the tones of a wind instrument. It's like a bassoon or a you know what I'm saying. So, there's 3 ways. You can close one end of the instrument, you can increase the length of the instrument, or you can increase the amount of the fraction of sound leaving the instrument. All 3 of these things either change the wavelength or the wave speed, and either one you get a change in frequency, which is just like in string instruments, what controls the pitch of the noise that's generated. When the pitch increases, the frequency increases as well. Something tells me that's correct. So if you close off one end of the wind instrument, then you only get 1 full wave in the object, whereas when the tube is open, you get 1/2 of the wave that fits inside the object, thus change the wavelength, and that's how we change the frequency. And that's it for today's video. Thank you for watching. Have a nice evening.
Alright, so last little part here, and I'll try to get through it pretty quick. So finally, we're going to talk about Snell's law and the law of refraction. So Snell's law states that the sines of the angles of incidence and refraction are equivalent to the reciprocal of the ratio of the indices of refraction. So words, that's a little confusing to hear. So here it is in the formula. There you go. N is the indices, and then sine of 1 is the angle of incidence, and the sine of 2 is the angle of refraction. So kind of what we just see in here in this is, if you look at this diagram here, kind of like when we saw the laser going into the prism, so the green line right there, the dashed line, is the normal. The black line is kind of just the basis and the interface. The red line, the P line, that's like your laser or your line, the light that's going through the thing that's being refracted. So right here we have our angle of incidence. Right here we have our angle of refraction, and then here we have our indices, N1 and N2. So basically what you're just seeing with this is that and also the indices are unitless and they change between each medium. So depending on your medium, then you'll be able to know one or more of the index of refraction. So then you'll be able. So then when you know the signs, then you can be able to solve for the other one. So this is helpful. First, we'll go to concave lenses. So the law of refraction is good with concave lenses, because so when you have light going through a concave lens, a virtual image is formed. You don't get a real image formed because the light scatters. As you can see with this diagram, the light scatters here from the focal point, which is right here, this black dot, and the light goes out. So this is helpful for people that are nearsighted, so to say they have the lenses that they have are concave, because it helps the light come in more so they can see things that are farther away, because it makes the object that is farther away seem smaller and clearer. So no real image is formed with these, and the object is always seen to be smaller with these lenses. So, and they're normally, again, upside down, which is similar with all mirrors and lenses. Now we're going to go on. So this happens because there's really little refraction that goes on inside of the lens. A lot of the, as you can, from the diagram, a lot of the light that comes through comes from the focal point and then reflects it up through the lens, not down to a central point outside of the lens, so you don't have the light that comes together to form a real image. So yeah, we'll move on to the convex images now, the convex lenses. So convex lenses are the lenses that we use with cameras and movie theaters and stuff. They create real images, and depending on where the object is in relation to the lens, that decides how big or small the image is going to be. So if you look here at this diagram, these lines right here, the blue lines, are parallel to the principal axis and then go through the lens, and the lens refracts the light beams to the focal point on the other side of the lens, which, as you can see from the green arrows, come together and they're inverted. So that's where you get the inversion of the images, which is why you always have to put things upside down in like a movie theater camera. So and then with the object, the images depends on where the object is. If you have the object that's farther than the 2F point, then the image is going to be smaller and inverted from the object. But if the object is between the 2F point and the F point, then the image is going to be larger and still inverted. But if the object is closer to the lens than the focal point, then you get a virtual image that is formed, and the image is upright. So yeah, I think that covers it all. So yeah, thank you guys for watching.